Thank you for being with us today. I'm happy to see all of you on site and online. This is a new seminar series we're trying out. It's called CIS Get to Know Your Industry Partner. We're happy to see so many online and offline with us. With this new seminar series, we strive to promote the exchange between enterprises and companies and research groups active in the field of intelligent systems. Today, we're delighted to have Laurent Daudet with us. He's the CTO and co-founder at LightOn, a startup he co-founded in 2016. He's going to give us a talk entitled Photonic Computing for Massively Parallel AI. To give you an idea of what to expect, Laurent is going to speak for 40 to 45 minutes, and then we'll have roughly 15 to 20 minutes of time for questions. If you are online, please don't hesitate to put your questions in the chat. I will try to take them up later on, but if you're on site, that's going to be easier to manage. I'd like to thank Laurent for his availability. He came in from Paris, I understand. And I'd like to thank again the entire CIS team for preparing the event. Laurent, the floor is all yours.
Thank you. Thank you for the intro and for the invitation to give this presentation. Yeah, so of course, as a CTO, I do not understand anything technical. I'm just managing a group of fantastic people. And so the team of LightOn is about 25 people now. We are based in Paris, and we have 4 co-founders, including Igor, CEO, and we have 2 scientific advisors, including Florent Jacala, who is here in the room, who is also professor at EPFL, and Sylvain Gigant, who is our optics advisor. So just as an introduction to the topic, now there is this new generation of AI, and I'm sure most of you are already familiar with that, but it keeps amazing me, like the progress it has made in the recent years. You prompt a language model like this, write a professional email to Tom Sanders, a salesman for a laser company, and here's what this language model, this new generation of language model, produce automatically. Here, if you see what's being produced automatically, it's a perfect email, something that you would write. It's very good English. It has invented a way of using the laser, and if you're a trigger, it may invent something else. But it's, yeah, I mean, it's really perfect in terms of output. And you can do even things even more sophisticated, like writing a creative ad for a product to run on Facebook, and you just see what type of product it is. And you prompt it. This is the ad I wrote for Facebook, aimed at teenage girls. So you give the type of target audience, and being the thing generate automatically some like 3 lines of content for your ad, a personalized ad, exactly in style and in content. And okay, these are the model in English, but of course at LightOn we did it in French, and this is just an example for those who can read French. We took the first lines are just the Figaro newspaper about real estate in Paris or whatever, and then you click on generate, and we have this example, like if you type pagnol.lighton.ai online, you can play with it. It generates text. You prompt it with French, and then it would continue forever. And it's I think it's really amazing in a sense that not only it stays in the same type of content, it's about real estate in Paris, but also it understood the style, like quoting some experts, like the algorithm invented some guy called Eric Legendre. There's no Eric Legendre in real life, just the algorithm invented some guy and quoted the guy like an expert, exactly like in the prompt, where the prompt quoted the expert guys in this area of real estate. So these text generation capabilities are, I think, really new. These things appear with GPT-3 a year and a half ago, and it really triggers a new generation that we call the transformative AI. And for us, transformative AI is this new generation to understand text, of course, still with quotes, because it's still a stupid machine, but it's so big that it's the fact that it's stupid goes a bit further away. And it can generate text in the right topic and style, as I said. Yes, and something also new compared to the machine learning that we used to do even just a few years ago. You were told, yeah, to do machine learning, you need to have super labeled data. So you were doing supervised training with a lot of labeled data, and you would learn how to distinguish cats and dogs and so on with labeled data. And now the data is no more labeled. You just put in text, all the text you have. And when I ask my engineer, do you prefer books or newspaper articles or internet dump? They say, no, I take everything. Just everything you have, and so that they say it's civilization scale. It's like you take everything that's available in a given language to train the model. Unlabeled data, raw unlabeled data, and the model learns by itself the categories, the meaning, and so on. So that's what the people at Stanford call this type of model foundation models, in a sense that they are these models you don't define the task to do. First, you build a language model, and then you interact with it in different manners. And especially that after at some certain parameter size, like above 10 billion type of parameters, you start to emerge some capabilities like what's called few-shot learning, or even zero-shot learning, is that doing tasks that have not been explicitly trained for, like making summaries of text or this Facebook ad type of things. Or this model has its own life and behaves like you would ask the model to do something to rewrite, or you can ask questions to the model and so on. So you interact with the model like it becomes a thing, like a living object. You not living, of course, but it's so it's really amazing, these capabilities. And of course, people are very excited now about doing this type of model for not only images, of course, but proteins. This is really the big thing now. With Google has a big initiative in this type of transformer model for protein, computer code as well, like suggesting completion for computer code. It starts to work very well. And of course, there is a lot of investment in many research labs, and especially also for businesses. All the big giants, either the American or the Chinese, invest massively in this type of models because they believe it will disrupt maybe a lot of services. Automation in services is like one of the goals. But what people don't talk so much is the hidden ingredient is really there's a huge barrier to entry in the amount of compute that you need for that. When I say you need massive amount of text, of course, it also goes with massive amount of compute. Just now we are entering a new era where to train machine learning, this type of models, you need a supercomputer just to do that, running for days, which is like something that also changes the architecture of supercomputer. In the past, people were doing like weather forecast type of things, but now when I'm talking to people running supercomputer, they say no, the demand is completely shifting to this type of models. So just to give you orders of magnitude, GPT-3 required 3 million GPU hours, and what was 2 years ago the state-of-the-art GPU V100, like 500 tons of carbon dioxide in equivalent type of energy, on an estimated price of between $5 and $10 million, the equivalent if you were to train that at the cloud prices. So this is just insane, the size of this model, the amount of energy and computing capabilities that they require. But it's only the beginning. I mean, the models, GPT-3 is now small compared to other models that have appeared since then. And why? Why finally this AI model increased much faster than Moore's law. People have estimated that the number of parameters in this model double every 3 months, which is, of course, much faster than any Moore's law that you can imagine. And the reason is, well, at the moment, people believe in these scaling laws for language model. It's a theory that says that for certain classes of models, such as these ones, you can really predict on many orders of magnitude the performance as a function of the number of parameters. So this type of scaling laws that has been used in engineering for decades, now they come now in this type of models as well. And it's really, I mean, you can see, for instance, interesting things like sometimes it's better to have a larger model, but to undertrain it rather to have a smaller model, but go to convergence. I mean, it's a fact that has been well known empirically by some practitioners, but now people are able to put some numbers on that just to really calibrate the parameter size as a function of how much compute you have and how much training data you have. And the bottom line is that, of course, the larger model within that paradigm generalize better and train faster. So this is what's called the bitter lesson by Rich Sutton. Here, in these classes of model, for a given architecture, the bigger you go, the better you are. And so now you have models that are already 10 times bigger than GPT-3. And still, models are getting bigger and bigger, and we don't know where it's going to stop. At some point, it's going to stop, of course. But so, as I said, the hardware is really becoming really a bottleneck, a barrier to entry. There are many, even academic people, who cannot train these models because they don't have access to these supercomputers. And when we started LightOn 5 years ago, people said, "You're crazy. I mean, computer hardware is completely commoditized, and people are happy with CPU and GPU, and that's it. Why do you want to do specialized chip?" But at that time, that was what we call the Cambrian explosion of AI chips. And there were tens of projects about designing better chips to handle this type of workloads. And interestingly, all the big companies, like even like Tesla has its own AI chip, and with Igor last week, we found out that 8 out of 10 largest companies in the world have their own AI chip. So it's really something that's really remarkable, we believe. And amongst them, of course, most of them are on silicon, but we believe that light-based computing, photonic computing, maybe has an important role to play in a future architecture. Of course, quantum is a big topic at the moment. There are lots of projects in quantum, but we still believe that before quantum really scales up to the size where it's going to be really useful, which may take quite some time, we believe that classical optics with just wave interference, but not quantum, is already something that's interesting that can be used nowadays, as I will try to convince you now. And it's interesting just to step back a little bit and to look at history and how like optical processing of information is a really old idea. I mean, we were able to trace some ideas back in the 1930s where, okay, they were not computing with light. It was like a mechanical or electrical device to do some computation. They were just using light to check that the computation was finished. So they were aligning some wheels to do some, I think, some number factorization type of thing. So light was used in a way in the computation, but I think of course the real boom went after World War II, the first digital computers and so on. At that time, people realized that a lens makes a Fourier transform for free. A lens is a Fourier transformer. So it's fantastic. You can use a lens to do, if you have a Fourier transform, you have correlation and you have convolution. So you have all this sort of pattern matching that, of course, many people were interested in. If you do radar, if you want to do satellite images, of course, there was a lot of funding coming from the defense industry to put, they were even putting some of this photonic correlator in satellites to do amazing technology at that time. And even there was a work here from scientists from the 80s, so well-known expert, of course, in EPFL, and amazing technology. I mean, we only reinvent what has been done in the past. It's always like that in history, but it's really important, I think, to acknowledge what has been done in the past. This technology has been very active in the 70s, in the 80s, but in the 90s, because of Moore's law, really, I believe this is one important reason. Of course, there may be other reasons, but the computer chips progressed so fast in the 90s that it was harder, I believe, to be competitive, really, in terms of computation compared to what people could do on chips. And we believe, like, past these ages, and know there's a revival of optical computing maybe throughout the world. There are many projects because, I mean, as I said, there's a need, really a need for much more efficient compute, not only more power efficient and so on, but also the fact that the algorithm that can handle much better now, I believe, the low precision. If you do analog computing, if you do photonic computing, you are really bound with low precision. Well, with machine learning, fundamentally, this is statistics on noisy data. So it's really, really robust to this type of low precision. And I believe this is a very, very good application of this type of technologies. So I believe we are now in a new, I would say, golden age of optical processing. So I'm going to now discuss more about LightOn. And of course, from this introduction, you may have this idea that we had this grand vision to start the company, but not at all. We started LightOn like any good scientific project. We started LightOn just with coffee and discussing with friends and colleagues from the lab. So we did not at all have the idea of making a company. It was like I was reading this blog that some of you may know called Nuit Blanche about this link between sensing and machine learning and information processing and so on. And so the guy behind Nuit Blanche is called Igor. And so I was discussing with him, and one day, we were discussing about this idea of compressive sensing. And I'm going to skip. I'm not going to explain what is compressive sensing. Just have to. This is some linear algebra type of thing. How to sample a signal at the level of information as close as possible to the information content. And one good way of doing that was by using random matrices. So using random matrices, it's a good way to go beyond Nyquist sampling by making some further assumption on the signal, but you could be much more efficient than what the Shannon-Nyquist sampling tells you in terms of acquiring signals. So it's a good way of using random matrices, what's called random projection. It's multiplying the signal by random matrices. And then one day, Igor sent me an email and said, hey, we should go and talk to Sylvain, who is, he was at that time, Sylvain was in the same university, but in a different building. I was doing acoustics, Sylvain was doing optics. No way I was going to talk to some optics guy. I mean, this, you are in your own domain, and why would I talk to Sylvain? And he goes, yes, we should go and talk to him because there are some random matrices in what Sylvain does. Well, okay, so let's go and let's have coffee with Sylvain, another guy to have coffee with. And so actually, what Sylvain does is he's an expert, one of the world experts in light transport in diffusive media. So diffusive media, and this is something that we experience every day, like light through. I mean, from my hometown is Marseille, so we have pastis, this drink where the light you cannot see through a glass of pastis. You can light goes through, but it's not It's not transparent. You cannot see it through. It's like mist, snow, or human tissues. And I particularly like this painting from de la Tour, where you have the light of the candle, and you see that some light goes through the fingers, but you don't see the bones, right? You don't see the shadow of the bones. So it means that something must have happened to the light, and actually what has happened is the light is completely scattered. So there is no photon that travels in a straight line. All the photons, some of them go out eventually, but they all go a very complicated path of multiple scattering, and eventually some of them go out. And the question these people ask is, how deep can you see through this scattering material? And actually, classical physics tells you that because of this multiple scattering through human tissues, for instance, you cannot see very deep. There is fundamental limitation called Beer-Lambert law that tells you that ballistic light decays exponentially. So after a couple of millimeters, you are completely buried in noise. There is no more signal-to-noise ratio, and it's completely hopeless to image through more than a couple of millimeters through human tissues. But actually, if you use coherent light, there are some further things that you can do. And that was what Sylvain was doing at that time, using coherent light to go beyond these fundamental limitations of classical analysis of light scattering. So the very simple experiment, you take a laser beam on a scattering material, imagine like a layer of white paint, for instance, and you project on a wall. What you see is what's called speckle. So speckle is this type of interference pattern that you see, where it is just secondary sources at the outside of the material. They would interfere constructively or destructively, and they would give you this speckle phenomena. It's well known for people doing radar, for instance, people doing ultrasound imaging, everyone working with a coherent wave. They see this speckle phenomena, and usually they consider speckle as a nuisance. They want to reduce speckle because it's not where the information is. So for them, it's like all this reducing speckle. It's a goal in life for them. And now what Sylvain was doing in his lab was to generalize this experiment. So instead of having a uniform beam, you would modulate spatially, meaning you just have to project an image, project some information. So you take a spatial light modulator. A spatial light modulator, this is a device that you would have in the video projector, like the one we have in the room here. This is just, I mean, there are many technologies, but the one you can employ is this beautiful, amazing MEMS technology by Texas Instruments called a DMD, digital micromirror device. This is just an array of millions of small mirrors that can flip very fast in two positions that you can address individually. So fundamentally, spatial light modulator is a way to put 1 megabit of information or several megabits of information as an image, and then you use your light beam to carry that information. You go on the scattering slab, and you image that with a CMOS camera. And because the physics is linear, there is no nonlinear propagation, then there must be, if you consider discrete input, discrete set of pixels at input and output, there must be a linear relationship between the two, between input and output. So if you know this matrix H, this transmission matrix H, you have completely characterized, at least in this set of discrete pixels, what has happened. And actually, scattering becomes a deterministic process now. It's completely deterministic. H, it's one draw of a random process due to the position of the scatterers, but once the position of the scatterer are fixed, then it becomes a deterministic process. You can really you can predict what will be the output for a given input now. If you know H, you know everything about the system. Okay, there is one caveat, which is the fact that you have a pointwise and element-wise nonlinearity because the electromagnetic field is complex valued, and you measure an intensity, which is the square modulus of the field. Okay, I'll come back to that later. So basically, what we learned by talking to Sylvain was that scattering actually as opposed to what people were thinking, I believe, it's like scattering does not lose the information. It's mixed, but it's there, and it's actually optimal in a certain sense, in a sense that compressive sensing was imagining before with this new theory, and it's and actually, yeah, as we've seen, it's a matrix vector multiplication followed by a nonlinearity, the one that you have at the sensing stage. And we knew it was a good idea maybe to see if there was a link with machine learning, because of course deep learning is just stacking matrix vector multiplication with nonlinearity. So so that's when we started to talk to the fourth musketeer in the team, who is Laurent, who is an expert in machine learning, and we went to see Laurent and say, okay, I have a machine that does random projection optically. Is that useful? And of course, he said, yeah, of course, that's useful. You can do some mixing precondition information, and there's a lot of application, and this is all due to this beautiful theory, this Johnson-Linus-Strauss lemma that tells you that fundamentally random projection preserve angles, they preserve distances up to some error that you can control. So this is a good way of expanding a vector to embed in higher dimensional spaces, like as a kernel machine, or reduce the dimensionality of the vector. You can compress using random matrices in order to do machine learning in the compressed domain if you want to save space and so on. So there are many uses of this random projection in machine learning. So actually, we were on the four of us were sitting around the table, and we have this machine that does random projection, an operation that nominally order of n square complexity, and now we have a physical device that does it order of one complexity, up to very large vector size. And we were thinking, does it change actually computing pipelines? And can we engineer it so that it has economic value, because it's a machine to do some computation, and maybe so we were just to see if we just take the components that we have in the experiment, can we push these optoelectronic components to their limits, and how many computation per second can it do? And okay, in terms of number of pixels, take the technology, as I said, DMD technology from TI. Now you have video projector for 8K movie with 32 million pixels, so it's like millions of pixels. And so the input is vectors of size that can scale up to 32 million at the moment, with technology that you can buy really off the shelf. The output, that's the same. We all have digital camera with tens, even hundreds, sometimes of millions of pixels. So the output again can scale to millions, tens of millions, even hundreds of millions for the largest ones. So it means that in terms of metrics, if you think of matrix vector multiplication, the matrix has much more than trillions of independent random coefficients. And I say independent, of course, to make them really independent, there is a lot of expertise, because if you do it just in a standard way, they would be correlated and they would be not completely uniform. But if you manage well the optics, the distribution of the random coefficient can be really IID, Gaussian IID. So you have this matrix that's Gaussian IID that you cannot change. So it's fixed by design, but it's like a memory, terabytes of memory that you can access with light, that you can read with light, literally at the speed of light. Of course, you are still bound by input-output of the data, but accessing the data is at the speed of light, and at no energy cost, because it's this light scattering is passive. It's a passive phenomenon. And of course, again, you need energy to enter the data and to get the data out. So there's no magic. You're still physics is still you're not breaking any law of physics here. So eventually, what we call optical processing unit. Now we call this technology OPU, optical processing unit. It's a machine that does random projection in the analog domain. So where you take an input vector x and you output the result of the multiplication of x by a fixed by design random matrix h. So this is something that does only one thing. Okay, so there's one thing. we manage with some interferometry tricks to get rid of the nonlinearity if you want. If you're happy with the nonlinearity, if you do machine learning, then it's fine. Keep the nonlinearity. But sometimes in some of the applications that I will detail later, you want to have the linear transform, and with some interferometry tricks, so we remove that if in a transparent way. Yeah, also in terms of speed, I believe in this video projector that we have here, the DMD would flip the mirror at about 20 kilohertz. So this is about the nominal speed at which this MEMS modulator go. So it means you can really run these devices at the kilohertz rates on maybe tens of kilohertz. So if you just multiply these numbers just to see the equivalent number of operations, it's 10 to the power 15 operations per second, which is impressive compared to what the GPU does. It's faster than the GPU in terms of maybe 1 to 2 orders of magnitude better than a GPU. But of course, they are not comparable because they are not programmable here. It's not first, it's not flops. It's ops in the analog domain, so it's reduced precision. They are not flops, but I have to say that the high-end GPUs now also go to reduced precision, like the high number of operations that they give is only for reduced precision, like this new low precision format. They even have some int4 type of formats now, the latest GPUs. But yeah, they are non-programmable. I would say people say it's a non-Feynman type of computing where you cannot tune the coefficients of the random matrix. They are fixed by design. So you trade off the size by the programmability. So it's a different trade-off compared to the standard computing hardware that you would have. But let's see if it's useful now. So fast forward 5 years, we went from an experiment in the optics in Sylvain's lab on an optics table like a 1 square meter to first like a shoebox type of experiment, and now inside the box what we call the photonic core, which is really where the multiplication happens. It has about the size of this smartphone, a bit thicker here, so it's really much more compact. So inside the box now we have this product, which is, I believe, the world's first photonic AI coprocessor. It's really a coprocessor. It does only this matrix vector multiplication. It plugs onto your server through external PCI Express. So it goes on a PCI Express slot like any GPU board. It does 1500 teraops for only 30 watts, which is in terms of operation per watt. I say it's not a one-to-one comparison. They are not the same type of operation, but just to give you an order of magnitude, it's 200 times better than the NVIDIA GPU boards. And of course, it's like reducing, at least measuring and having some ideas about the energy impact of machine learning is now getting more and more important, obviously. And also, I will come back to that later. There are some interesting properties in data privacy. We not only developed the hardware, but we also did a lot of effort in developing an API and an SDK that's as easy as possible for practitioners. We want people who are expert in machine learning to be able to play with the machine without knowing anything about photonics. So it's just a Python Python toolbox. You import the toolbox, and then you have one line of command. You send the data to the OPU, you get the result, and that's it. And there is no question about the saturation of the images and so on. There are 2-3 tricks you have to learn, but usually if you are already an expert in Python, it's compliant with PyTorch and scikit-learn and so on. If you already are familiar with that, you can do all your optimization, and usually in a couple of hours, people are able to use the machine and start to play with their own program. And the type of use cases. So I still haven't got to the point where how is it useful? And yes, it's useful in many framework, but really, I want to emphasize the fact that it's always hybrid. We don't replace GPUs. We are sitting next to the GPU. If you have some convolution to do them on GPUs. They are designed for that. They are super good at that. Keep that. But then if you go to the dense layers that require a lot of memory, then maybe the GPUs are not that good anymore. I mean, they are good, but not. Then you could beat them in dense matrices. And so these are just a few of the studies. We have a web page where we list all the studies that have been done either by LightOn engineer or by external users that have been connecting through, or we have a small cloud platform where some experts connect on the machine and try their algorithms on prototypes. For instance, we have David, who is an expert in data from CERN, trying to classify events. Is this a particle of certain type, and so on. So it's high-dimensional classification, and he was doing classification using our optical processing units. We've done some reinforcement learning, finding nearest neighbor states with this locality-sensitive hashing type of techniques that this random projection allow. Yeah, I'm going to come back about change-point detection later on. Reservoir computing as well. It's a relatively well-matched technique to do computations in time series. On the latest studies, I'll come back to that, are with collaboration with CTO or Facebook research on adversarial robustness or differential privacy by design. Okay, so some benchmark. Again, we don't, I mean, benchmark, you all know, we all do cherry picking for benchmark. So this is my cherry picking. Yes, this is my cherry picking for my benchmark where depending on the computations, I can have some speed up of up to 23 times. But really the bottom line is that because we replace an operation that order n squared by an operation that's order 1, the higher the dimension, the better you are in terms of comparison. So we are happy with when we are dealing with signals that are in extremely high dimension, 10,000, 100,000, 1 million, even more millions when we cascade things. Just one example, change point detection in high dimensional time series. For instance, you have some time series in high dimension, you want to detect some change point. Here I just took an illustration monitoring a data center. You have tens of thousands of signals, and you want to detect when something wrong happened. Maybe there was an attack, or maybe some processor that went wrong, or some router that went wrong, and so on at some point, and you want to detect that as early as possible. So one of our users, together with Jacopo, with our lead machine learning, came up with this algorithm to do change point detection using this sketching method that are now getting more and more familiar in machine learning. Sketching is like reducing the amount of information in the database so that you can still do your machine learning in the sketching domain. So you retain the characteristic that you want to keep for the problem at hand while reducing the amount of information. So you basically, for each new vector, you do the random projection to reduce the dimension, and then you add it to the sketch. It's like a moving average with some forgetting factor lambda. You do some moving average with lambda as a forgetting factor, and you build your sketch, you update your sketch at each time step, and so on. So extremely simple. Just each new information, you sketch it and you add it to your sketch, to the sketch, which is this small vector. And you actually do two sketches, one with a long forgetting factor, or one with a short forgetting factor. Long memory, short memory. And then you compare the two. You compare the two sketches. If the two sketches are similar, then probably the underlying distribution is stationary. But then when the fast time scale sketch start to move independently of the other one, it's probably something has happened. And the fact that you can guarantee with the physical laws that the distribution of the coefficient is Gaussian IID, you can have a really probabilistic bounds on the difference between the two. You can really do the math to the end. And just as an illustration, we did that for like a time series, which is like a video stream on like CCTV type of thing. We highlight in red superpixel that have been detected as where the algorithm detected there has been changes. So we are in dimension superpixel are 10 by 10, three channel of color. So we are in dimension 300. On each superpixel, yeah, here you detect the cars, and here it's interesting, you even detect the clouds passing over the parking lot. So it can be really sensitive. Yeah. So here we are in dimension 300, which is not per superpixel, which is not so high. But of course, you could do that in much higher dimension. As I said, the benefit comes, I'm going to skip that, yes. The benefit in computing time comes when the dimension is really large. If you see the purple, which is the computation time using the optical processing unit, I said it's essentially order 1. It's essentially a constant. Of course, there is a bit of linear data pre and post processing, but if you forget about this very, very small linear cost, essentially the computing time is independent of the dimension. So you can go up to 1 million dimension, and the computing time would be the same, which is a bit counterintuitive. I mean, if you have been doing computing, of course, you know that the computing time, even with fast method, it increases maybe with log n, but here it's essentially independent of time. So if you are in dimension 10,000, 100,000, 1 million, then you could be 2, 3, 4 orders of magnitude faster than the baseline method. Yeah, maybe the last example I will give is randomized numerical linear algebra, like beyond machine learning. Like for instance, you want to do SVD, singular value decomposition, but you're running out of memory. Like if you try it in MATLAB, after a certain dimension, MATLAB will say out of memory and then won't do anything. So if you're in that case, what you could do is to use randomized method. And to the randomized method, I'm going to give just the basic example with a randomized matrix multiplication. You want to multiply these two matrices A and B, and they are really large. And what you could do instead of doing the plain multiplication is to insert R transpose, where R is a random matrix. And of course, R transpose is approximately the identity. If it's Gaussian distributed, it's like a white noise. So autocorrelation of a white noise is the Dirac. In a way, this is an interpretation of this fact. So R transpose is approximately the identity. So you can insert that between A and B. And now you just see AR as a compressed version of A, R transpose B as a compressed version of B, and you multiply. You only have to do the multiplication of the two compressed matrices, right? So if you're able to do this multiplication by the green matrix very fast, then it's better because you only have to do the approximate multiplication in the compressed domain, right? And that's exactly what this optical processing unit does, is multiplying by a random matrix. So you could use this optical processing unit just as a compressor of information, and then you have you can multiply you can only multiply digitally on your CPU or GPU or on your preferred multiplication device in the compressed domain. Of course, this is just for illustration purposes. The approximation is lousy. It is not a good approximation here. I mean, but this is very simple to understand. What works much better is the SVD, randomized SVD, where you randomize the X with the random matrix. You do the SVD on a randomized matrix, and then by perturbation method, you can go, you can have the SVD of the full matrix, at least to an approximation where you can guarantee the error that you have some bounds on the error that you make. So this is a good way of making randomized SVD when the matrix is too large. And you can do a recommender system based on that. I'm going to skip that. Yeah, you can do randomized trace estimator as well. I'm going to skip that. If your signal lives on graph and you want to detect communities, you can get the trace of the cubic value of the adjacency matrix and count the number of communities, detect the communities in your graph. Yes. So eventually, there are some interesting properties. The fact that we are analog or noisy, first, you may think it's a limitation, but actually, it has some interesting properties that were not expected when we started the project. Actually, it gives you some nice properties like robustness to adversarial attacks, for instance. Just you know what adversarial attacks is. You have a picture on, you just put a bit of well-designed noise. Of course, you design it such a way to fool your algorithm. And here, of course, a pig is being classified as an airliner here. If you have chosen that, and I mean, this is a well-known problem for classification issues. And of course, we are all going to have self-driving car in the near future, and you don't want a self-driving car to make such mistakes, at least as long as they do such mistakes. I'm not going into one. What we came up with is to use this optical hardware at the end of your classification. And you retrain your network with some training technique called DFA that's well adapted to that. The fact that you cannot completely characterize the optical up to infinite precision gives you some good properties with respect to adversarial attacks against. So there are two types of attacks: white box, if you have completely access to the system; black box, if you can only probe the system. But anyway, I mean, we have this article on archive that you can use. And what's nice as well, it can also boost already robust model. You can just add that on top of existing adversarial robustness adversarial attack model, and it gives you a boost in performance. Also, again, the latest that has been accepted and is going to be presented at next NeurIPS. I think I can disclose that now. Is in collaboration with CTO, and it's about differential privacy as well. Differential privacy, same type of, you train a neural network on sensitive data like medical record, and you want to train a model, but not from the model. You don't want people to have access to individual files because they are sensitive, they are private. So again, the fact that you have noise in the system gives you privacy by design. Yeah, 2 minutes. And so on. So just to conclude, I started with a GPT-3, and now I think it's very far. I mean, I went to many applications, but really the question is, okay, why did you talk about GPT-3? Was you can do? I mean, differential privacy is nice, but can you do something for GPT-3? Okay, maybe. So first, we have trained some GPT-3. But on standard GPU, so on a supercomputer in France. So we have trained this Pagnol model. You can play with the demo, as I said, just to understand where the bottlenecks were in the training of this computation. But it also has economic value. Using this training method, we also discovered this alternative to backpropagation that use random projection. This technology called direct feedback alignment, where we output the error back to the deep layers in a distributed fashion. So you avoid the sequential aspect of backpropagation, which is great, unless when you start to scale to a whole supercomputer, all your nodes keep exchanging some information, and eventually you are often limited by the capacity to exchange information rather than the computing capacity. So this technology might be a way to alleviate these bottlenecks in the future. So we have at the moment proven that we can train mini GPT optically. We have done it. Of course, it's a small scale, so there is no real benefit in terms of speed. We are working on that. And one way to work on that is to to put our optical processing unit on a real supercomputer. We have to do it. You cannot train GPT-3 on a normal computer. You need to have a supercomputer. So I'm very proud to disclose that in 2 weeks' time, we will be putting one of our optical processing units on a French research supercomputer, which is called Janzé. And we hope to be able to train a much larger language model on that using our optical device. So I guess you will hear, if we are successful, you will hear from that. So by way of conclusion, I really like this paper by Sarah Hooker, who is research engineer at Google, and that was, I mean, this idea on how tooling, on that, especially true in machine learning, that we are completely constrained by the tools we use, and for the research ideas that we that are successful eventually. And so we have this way of thinking that's completely driven by the tools. And of course, we are not rigging this lottery, hardware lottery. We are just buying new tickets. So I'm trying to convince you that this optical processing unit is a good way of playing with new hardware and maybe have new research ideas because you have new hardware, non-Feynman computing, and it's very easy to do. I think this is the first, the key lesson is if you want to play, you don't have to be an expert in photonics. It's there. It's on the market. Just get one and have fun. And we try to build also a community. So we have plenty of resources on GitHub and so on. So that's why I like to talk to universities. Is many researchers have many bright ideas that we've never thought of, and that's how we can learn what to do with this photonic computing device. Thank you.
So please let me say some words of closing. Thank you so much, Laurent, for your talk today. Thanks to all of you for being online and offline with us. Just a quick heads up, next week, Monday and Tuesday, we would be delighted to actually see you for the EPFL CIS Digital Twin Days. You can participate either online, just go to QR code, or you can be with us at the Swiss Tech Convention Center in Lausanne. Get your tickets rapidly, please. We have roughly 20 tickets left for on-site, so get them as soon as you can if you want to be with us. Then on the 29th of November, we will look forward to welcome Professor Herzog for his Get to Know Your Neighbor talk. Then for the 6th of December, we are looking forward to see Mark Pauli explaining us what he's up to with his work in his lab. Thank you all, and we hope to see you soon at our next events. Stay safe and goodbye.